Greetings, this is Paul Bamberg with the introductory lecture for the first class in Math 117 on exponentials and compound interest. We'll generally use the symbol R to refer to the annual interest rate, and the simplest context in which to apply this is what you've heard of as simple interest. If you apply interest at a rate R for an interval of 10 years, for t years, $1 will grow to 1 plus R times t dollars. As a practical matter, this only works if the borrower has to wait until time t has elapsed in order to claim the interest. Otherwise, she'll withdraw the money partway through, collecting interest on it, and reinvest the larger amount. And that brings us to compound interest. We could break up our interval into n subintervals. Each of those will, of course, have a length t over n. In one subinterval, the balance will be multiplied by a factor of 1 plus r times t over n. And since this will happen n times, we have to raise that to the nth power to figure out the final amount to which the original deposit has grown. As long as you can say the borrower can only collect the money on the first day of the month or something like that, this is perfectly reasonable. Mathematically, it's actually much simpler to imagine continuously compounded interest. We make the subintervals shorter and shorter while making them more numerous, and then we let the number of subintervals n approach infinity, and now we see that $1 grows to the limit of 1 plus rt over n to the nth power as n approaches infinity, and that limit is equal to the exponential function e to the rt. When you're comparing various schemes for collecting interest, sometimes a useful figure to have in mind is the amount to which $1 would increase over a period of 1 year. For simple interest, that is just 1 plus r, but if you have compound interest, it becomes a bit larger, and for continuously compounded interest, where it will grow from $1 to e to the rt dollars, the amount by which $1 will increase is not r, it's e to the r minus 1, which is a little bit larger than r itself. It's straightforward to approach this problem of interest in terms of differential equations. Let's let capital A denote the balance in an interest-bearing account, and the interest rate is the rate at which it grows. So the rate of increase, a prime of t, is equal to the interest rate, r, times the balance, a. And in this context, it would be perfectly reasonable to consider an interest rate that was not constant, but a function of time. We could also consider making deposits into that account at a rate h of t, and in that case, the rate of increase in the balance in the account, a prime of t, will equal r of t times a of t, that's the effect of interest, plus h of t, which is the effect of making deposits. In either of these two cases, we have a first-order differential equation, something that relates the derivative a prime to a itself, and these are equations that are easy to solve. First, let's consider what mathematicians like to call the homogeneous equation, where you don't have any extra deposits. Every term either involves the derivative f prime of the function or the function f itself. In that case, as you may have learned in a first course in calculus, you can do what's called separating variables. Rewrite this as f prime over f equals r times t. You integrate both sides. The integral of f prime over f is the natural logarithm of f, and we get log f at time t minus log f at time 0 is equal to the integral of the right-hand side from 0 to t. Notice that in this case, there's no requirement that r has to be a constant, and it's kind of interesting that all that matters is the integral of the interest rate over the period from 0 to capital T. It doesn't make any difference whether the interest rate is large at the beginning and small at the end, small at the beginning and large at the end, or constant throughout. Now we can take the exponential of both sides of this equation. The exponential of the log of f of t is, of course, f of t itself. On the other side, we have the exponential of log of f of 0. That's f of 0, the initial deposit, and that gets multiplied by the exponential of the interest rate integrated over the time period. Most of the time, r of t is constant, and we have the well-known formula that if you start with an amount f of 0 as your initial deposit, after time capital T has elapsed, that will increase to f of 0 times e to the rt. Now let's tackle the slightly more complicated situation where we're making deposits and have an inhomogeneous equation. Inhomogeneous because we've got this extra term h of t representing the rate at which deposits are made that doesn't involve the balance capital A directly. There's a well-known trick for solving these problems. You let f of t be the solution of the homogeneous equation without the h. So in that case, f prime of t will just equal the interest rate times f itself, and then the trick is to set the balance equal to some function little a, which will have to be determined, times f of t. You may have seen this somewhere else. It's known as the variation of parameters trick, and it always works. Why does it work? Well, let's differentiate this equation. A prime of t from the left-hand side is, by the product rule, a prime times f plus a times f prime, and that has to equal the right-hand side. That's r of t times capital A of t, or r of t times little a of t times f of t, plus h of t. But f is a solution to the homogeneous equation. In other words, f prime is equal to little r times f, and that means that this term and this term are exactly the same. They cancel out, and we now have an equation a prime times f equals h. We can solve that for a prime. A prime equals h over f, and now with any luck we can find the antiderivative of a prime and determine the function a. But in principle, this function always exists. We've solved the problem. The balance is the function little a times f. Now, in fact, there's a way of looking at this that never requires you to mention differential equations, and we will be using this approach over and over again in this course. If you take a course in differential equations like Math 110, you will discover that this is the so-called Green's function solution to this differential equation. But in economic terms, this is so straightforward that most people just regard it as obvious. What do we know? We know that if we've got a constant interest rate r, a balance A will grow by a factor of e to the rt over time t. And in this case, we want to assume that the interest rate r is a constant. Why? Because then only the length of the interval matters. Now let's assume that we're making deposits into our account at a rate h of t. Each deposit will have the opportunity to grow over a time interval capital T minus little t. That's the time that elapses between the time little t at which the deposit is made and the time capital T at which we're computing the balance. And if we simply integrate over time, we see that the final balance will be the integral of h of t, the rate of deposit, multiplied by e to the r times capital T minus little t, the exponential growth factor. Why is this nice? Well, first, there's no differential equation to solve, which most people regard as an advantage. Second, and probably more importantly, money is not generally deposited continuously into a bank account. Usually there are discrete deposits made, and this approach just works fine if the deposits are made at discrete times instead of continuously. You just end up doing a sum in terms of an integral. Here's another way of looking at exponential growth, which will be very, very important when we're considering prices of call options. Suppose we have the opportunity to receive some amount, capital A, in the future, a time little t from now. Alternatively, we could say, why don't you give me a smaller amount, a times e to the minus rt now. I'll put it in the bank. It will increase in value by e to the plus rt, and after time t, it will be worth capital A. This is a nice way of figuring out the total value of payments that we are going to receive. If we're getting payments in the future, we have to discount them in order to assess their present value. And in fact, we can write this as an integral. If someone is proposing to pay us in the future at the rate h of t, we merely discount each of these deposits by the factor e to the minus rt, integrate from 0 to capital T, and this gives us the present day value of the future payments. As you'll see when we start working problems with this approach will work fine even if the payments are made discretely, and that's what happens typically with bonds, which will pay you a certain amount, say, once a year, or with annuities. Here's an interesting approach which we actually won't be following up on very thoroughly, but it's a way of looking at the problem where the discrete case fits in very neatly. We know that the rate at which a balance in an account grows because of compounded interest is r of t times a of t, and we're making deposits at a rate h. So now we can integrate over the time interval from 0 to capital T. Integrating the rate at which the balance increases, we get balance at time capital T minus balance at time 0, and that growth is the sum of two terms. The first is growth due to collecting interest, and we can calculate that by just taking r of t times capital A of t at all times between 0 and capital T and integrating. And the balance also grows because we're putting in deposits at the rate h of t. This is what's known as an integral equation because, as you'll see, the function a, which is unknown, appears on both sides of the equation. If capital A is a differentiable function, we can immediately turn this into a differential equation. Let's have a shot at that. The derivative of capital A is a prime. A of 0 is a constant. That drops out. The derivative of a definite integral with respect to its upper limit is just the integrand at the upper limit. So the first term has a derivative r of capital T times a of capital T, and the second term is h of capital T, and this is the differential equation that describes an interest-bearing bank account. If we make the deposits not continuously but at discrete times, then a of t is not a differentiable function, it's not even a continuous function. But the integral equation approach still works. It's still true that the increase in the balance capital A is the increase due to collecting interest plus now the sum rather than the integral of all deposits. Now let's review a formula that will let us figure out what happens if we collect a number of equally spaced payments or make a number of equally spaced deposits. Let's suppose we make deposits once a year. Each deposit is in the amount $B, and we are going to do this for capital N years into an account where the interest is compounded annually. Then it's easy to write down a formula for the final balance in the account. The final deposit, I equals 0, will be B, and that won't have accumulated any interest. The deposit made 1 year ago, I equals 1, will have been multiplied by 1 plus R, the amount to which it grows over that year raised to the first power. The deposit made 2 years ago will have increased to B times 1 plus R squared, and so on. And all we have to do is sum this series. You learned how to do this in high school. This is a finite geometric series, and the relevant formula is that the sum of x to the I from I equals 0 to n minus 1 is x to the n minus 1 over x minus 1. If you want a little practice in doing proof by induction, you might try proving this formula for yourself. Okay, in our case, x is equal to 1 plus r, and here is our very useful answer. If you are collecting interest compounded annually and you make a deposit of amount B for each of n years, the final balance in the account is B multiplied by 1 plus r to the nth minus 1 divided by r. Finally, a bit of mathematical nicety. How are we actually defining the exponential function? Well, the definition used in the Dineen textbook is that the exponential function is defined by its Taylor series. It's the sum from I equals 0 to infinity of x to the ith power over I factorial. Once we've made this definition for the exponential function, we can define the natural logarithm function to be the inverse of the exponential function. That is, if y is equal to the exponential of x, x is given as the inverse function, natural logarithm times y. Incidentally, in this course, all logarithms are natural logarithms. We will never use log to the base 10. Sometimes I will write log, sometimes I will write ln, but all logarithms are natural. Once you've made this definition, it's not too hard to prove all the basic properties of the exponential function, and you may actually have done this in an earlier calculus course. First, the exponential function is equal to its own derivative, and by the formula for differentiating an inverse function in general, the natural logarithm function g of y has the property that its derivative, as you already know, is 1 over I. By clever use of Taylor series, you can prove that the exponential of a sum is equal to the product of the exponentials. And finally, you can prove the limit formula for continuously compounded interest, that the limit of 1 plus t over n to the nth power, that's the growth factor if you divide into n subintervals and accumulate interest over each of them. The limit of that as n approaches infinity is the exponential of t. And I conclude with a word of warning. If your single variable calculus and your grasp of infinite series are so shaky that you say, I don't have a clue how I do this sort of proof. Maybe you're on the wrong course. Maybe you should take another math course where you do a bit more calculus and real analysis and come back next year. And with that comment, we are done.